LLMs, but for simulating user experience data, and that's going to be cool. So
Yes.
anyway.
Yeah. Thanks for the introduction. My name is Alireza. I'm gonna kind of continue where Thomas left off. So I'm gonna focus on how we can utilize LLMs, but in a very domain specific setting. And that is the experience sampling method, where we want to apply LLMs as programming assistants. So what is experience sampling method? So experience sampling method is, or ESM, is a popular research method that is used to understand what people do, feel, and think during their day-to-day activities through self-reporting. It has numerous applications, for example, in healthcare, where the health professionals want to assess the effectiveness of different health interventions, or in psychology, where psychologists want to study a specific psychological phenomena, or in user research as a way to, for example, let's say, measure user experience. So notifications as reminders play a very key role in this method because they're systematically sent and spread throughout the day in the day-to-day activities of the study participants, and that kind of offers a higher ecological validity. But, well, compared to, let's say, methods such as diary that are retrospective. But also, it's not a perfect solution, and it has also some issues, namely adherence. So, for example, the study participants drop out after a few weeks in the studies. And that is usually because the notifications can be intrusive or interruptive based on the activity they're doing. There are also other reasons, such as changes in motivation of the participants, etc. And these could result in low response rate in this type of research, and ultimately also lower quality research data. So, in other words, the way the, let's say, experimenters or people who work in this line of research make their protocols is usually based on their intuitions or the protocols that were used in the previous studies by their fellow researchers, what we call a classical ESM. But that usually results in suboptimal performance. On the other hand, we could also personalize at an individual level. Let's say we could personalize the timing of the notifications, etc., to kind of lower the dropouts and increase the response rate. But the problem in this domain is that there's a scarcity of open access ESM data that we can train on and build better models. And when we don't have that, then we typically are faced with a cold start, especially in the beginning of the learning process, which would in turn result in low compliance again. But if we had such data, we could then have a warm start, and then we could more meaningfully learn from the previous behaviors of the participants in these type of studies. Well, to address that, in our previous work, we designed a framework, including of a design phase, a simulation phase, and a real-time experiment phase, where the experimenters actually could play around with it, and we also made an interface with it, etc., called Sapphire, which is on GitHub, and they could kind of estimate what the participants will do in this type of studies. So specifically in the simulation phase, the type of researchers, let's say the social scientists, as an example, can in the design time get feedback and also estimate the agent behavior, in this case the participant behaviors, in terms of the response rate and dropouts when this method is applied. But the big problem after offering this type of a simulation in the domain was that typically social scientists are not really programmers, and when they want to make some expansions or make things a little bit more complicated, then they couldn't really do it because, well, they were not programmers and they required some programming knowledge. Well, typically when we face that problem, we could, handcraft different types of simulations. We could also think about like domain-specific languages. But, well, because of the popularity and the growth of the AI assistants, we wanted to take a look at them. We see that commercially, ChatGPT, Copilot, Google Gemini are being used. Also, we see that in our field, in HCI and HDI, we see also a growth in popularity in using this type of language models. So specifically, we want to use LLMs as enablers for our target audience, who are typically non-programmers, but they want to apply the ESM in their research. And our goal to do this study was to examine the capabilities and limitations of LLMs in this field, and also share our lessons that we learned along our journey. So in the future, when the different models and new updates come, then we can kind of have a benchmark and see where we stand compared to the past. Well, which is the present now. And also converse with the domain experts who would actually apply this in their day-to-day research and see what they feel about it. For that, we needed an example scenario. And basically, we wanted that scenario to be in such a way that the social scientists, let's say, would explain the agent behavior specifications in their natural language. And our job was to figure out what steps are needed to convert that into an executable simulation that would actually meet their demand. And of all the examples, we chose a simplistic example of, let's say, teachers' activity during day-to-day classes. In the school, they would teach, they would go on a break, they might receive notifications along the way, and based on their situation, they would answer it or not, and they do the self-reporting. We set this as our baseline simulation, baseline scenario for the simulation. And we kind of assessed it in two ways. So first, we wanted to work with LLMs through in-context learning and prompt engineering. And then we kind of showed it to our audience and see, through an interview, see how would they be able to use it. So for doing that, we would need an LLM. So we chose the OpenAI's GPT 3.5, Turbo 16K at the time. And this was basically the baseline prompt, our initial prompt that we used in our study, which is simulate teachers' activities during the day. Teachers will receive notifications on their smartphone every 2 hours. Then, depending on their situation, they either respond with a notification or ignore it. The program should estimate the response rate to such notifications for 50 teachers. We took a stepwise approach, and first we started with a zero-shot prompting, meaning that no examples were provided to the model. And then we did a one-shot prompt, and we asked the program to generate a full simulation code, and we gave that full simulation code as an example in the repository of other simulations that we handcrafted before. And then we took another approach, and for the one-shot prompting, and we had a tight structure, and we just wanted the GPT basically to program a specific snippet of that whole structure. And also, lastly, we wanted to do few-shot. We wanted to give as many examples as we can to the model, which we call iterative in-context learning. And to be able to do that effectively, we created our own tool called Prompt for Code. So, and that is the QR code to the GitHub repository if you're curious. And what this tool does is that it takes a directory full of source code of simulations. And given that they have well-formatted doc strings, it would dissect the doc strings and the source code, and then it would convert based on those doc strings of the module, of the functions, of the variables, and it would create a prompt in a natural language. And then it's going to combine that with the source code that was dissected and as an answer to that input prompt. And it would combine it with the input that comes from the user of this tool, and that would in turn generate the source code, then execute it and share the results to the user. So to do that, we followed some best practices in the field. So we asked our model to adopt a persona, we provided examples, and also we executed the output code, as I mentioned. And for each of those strategies that I mentioned before, we started iterating, and we stopped as soon as a similar output were generated in a successive turn. And to evaluate basically our results, We looked at whether the code could be executed as it was generated, were there any semantics error, were there any syntax error, and what actions were needed to be taken to actually fix the code from the way it was generated to the way that it could actually be ran and used. Details of which are all available in the paper, but also we have the outputs available in GitHub as examples. And then the summary of results looks like this, that the more structured we provided examples to the model, the better the quality of the code got. But it never got 100% correct. And in our research, our input was 7 simulation examples in the ESM domain with around 700 lines of code. And that was passed and parsed through the code through the tool that we made, prompt for code. We also did interviews with the experts in this field, social scientists, HCI researchers, and we did a thematic analysis while using the tool that we provided to them. And we identified 3 main themes, where the trust in LLM-based code generators, reliability and consistency, privacy and concerns popped out the most. I brought here a few quotes that the output of the LLMs is cool, but I need to validate it with an expert. Another participant said that I like to use the simulation to find the optimal number of notifications to my participants. Most behavior scientists don't code at all, so the tool has interesting potential for them. If I knew the details about what I want to simulate, I would code it myself. So some people were on the fence, some people liked it, some people not so much. Well, in the end, we could draw a few discussions and conclusion items, and I'd like to share that with you. That's my last slide. So one is instability and development. We see that LLMs are continuously evolving, which it calls for cautious interpretation of the code that is as the result of the output of the model. We all should always remember that these language models don't really have reasoning capabilities. And also they have variability in output, meaning you can't provide them the same input, the same information, but the output could be different each time. We did see a potential in optimization where systematic and automated prompt generation can increase the generated code quality. And we also see that it could save us times, and by us I mean the people who would work with this model. So for example, through prompt for code, we could just automatically generate a batch of prompts with the output code as examples to the system for in-context learning. We also got the expert feedback, as I shared with you. We saw some high enthusiasm. We also saw some not so high enthusiasm, but in general, they really liked the idea that they would, as the experts in the field, they could express this needs to some junior programmers, to their students, that they could work with and collaborate with, and they could kind of fast-track prototyping these type of simulations. And which leads kind of to this point, collaboration, which we think that the effective use of LLM-based code generators requires collaboration between non-technical, which are, let's say, those social scientists, and the technical expert, let's say, the software engineers. As I mentioned, there is a data deficiency in the domain that I've been working in during my PhD, and this way of training LLMs and synthesizing data could be a way to solve that issue. Also sharing tools like, for example, prompt for code, and also different type of design alternatives. What was the input? What was the output? We believe that is one of the best ways to kind of share these resources and be able to kind of push the boundaries and move forward in the field by sharing this information. Also, for future directions of research, we think that addressing existing concerns and leveraging LLMs for autonomous code checking, that is just one example, but can reshape the software development teams, allowing domain experts to contribute also more effectively in this way.
Questions?